Okay, welcome everyone to the Fluid Seminar this week. So I have the pleasure of introducing our speaker today, who's going to be Dr. Matthew Emes, who's a postdoctoral researcher at the University of Adelaide. So he's in the School of Mechanical Engineering. So Matthew completed his PhD in 2017 at the University of Adelaide, and he received the Dean's Commendation for Doctoral Thesis Excellence for his PhD thesis. And Matthew has a particular interest in experimental fluid mechanics and atmospheric boundary layer turbulence, and he's going to speak about that to us today a little bit. All right, so take it away, Matthew, if you want to do the screen share. Looks good. Yep, that all looks good for me. Perfect.
Thanks for the introduction, Kat. So today I'm going to present about some work in the Australian Solar Thermal Research Institute Heliostat project, which has been operational now for the last 6.5 years. So the title of the talk is Prediction of Structural Wind Loading and Aerodynamic Scaling Effects Due to Atmospheric Boundary Layer Turbulence. And this project has involved parties CSIRO, Australian National University in collaboration. And the project is funded by ARENA. And I'd like to acknowledge the other researchers in the aerodynamics research team from the University of Adelaide and also the Centre for Energy Technology within the School of Mechanical Engineering here, and their active contribution to some of the research I'll be discussing today and presenting today. In the fields of wind engineering, experimental fluid mechanics, and the aerodynamics of flat plates. So just a bit of background about the project. So concentrating solar thermal is the technology of this project, and it's an advancing renewable technology which is not at the level of levelized cost of electricity to be competitive with baseload power sources such as fossil fuels and even wind power and solar PV. As you can see, the heliostat field, which they're arranged in generally concentric or radial rows surrounding a central tower with a receiver at the top. They are arranged in rows surrounding that, and the capital cost of the materials to manufacture these heliostats contributes approximately 50% of the total cost of the plant, which is quite a significant portion. And the cost of each of these mirrors is approximately $150 per square meter of reflective area, where the principle of operation of the plant is for these heliostats to most efficiently track the solar radiation and reflect onto the receiver to maximize the thermal energy that can be collected. There's a few different programs, ASTRI being one of them around the world, which are working at developing research pathways to lower that LCOE I was mentioning, with a target of 12 cents per kilowatt hour. And the DOE Sunshot Initiative in the US similarly is targeting a more aggressive 6 cents per kilowatt hour, with the cost of the heliostat field to be reduced to $50 per meter squared by 2030. So why are we interested in these heliostats? Obviously, their cost is quite significant, but one of the factors that affects the cost in their design is the wind loads due to the atmospheric boundary layer turbulence during storms and gust fronts. It's very highly turbulent flow in these fields. They're very open and exposed to high wind events. And wind load prediction, obviously, it's a balancing act between if you are overestimating the loading, you will not have an optimized structure, and you'll be not getting the most cost-effective technology. However, one of the problems, as you can see in the video here, is that often some of the dynamic wind effects from the turbulence in the wind causes flutter vibrational effects, resonance, and ultimately can reduce the optical efficiency of the plant, which is which is a research area which has been pursued in multiple areas. So the motivation for the work is to reduce the cost of these mirrors, which can be simplified as a hinged flat plate exposed to highly turbulent flow in the lower atmospheric boundary layers. So as a one method that has been identified in the previous literature was to reduce the wind loads is to reduce the wind loads by considering, for example, on the left in the figure here, the operational and stow design wind speeds. So here, these design wind speeds represent the maximum wind speed of operation before which the heliostats are moved to the stow position when they are parked horizontally as a protective measure during storms and gust fronts. And it can be seen that the cost of the heliostats can be reduced by reducing this design wind speed. However, the site conditions, the turbulence within the field does dictate a lot into how far you can lower the design wind speed. As you can see in the right figure here, for different types of terrain roughness, low, L, medium, M, and H, high, generally, heliostats are designed for a medium roughness terrain, which can be characterized by an open country style, open flat terrain. Whereas, and as can be seen, with increasing heliostat size from 25 meters squared to 150 meters squared, the contribution of the support structure, comprising steel structure, trusses, torque tube, pedestal, increases from 18% of the total cost to 34% with an increasing heliostat size. So therefore, the effect of both wind speed and the turbulence characteristics in the atmospheric boundary layer are very important in the design of heliostats, and and optimization of these of this structure for wind load can therefore reduce the cost of the heliostats and therefore the concentrating solar technology. So as a brief outline of the presentation, I'll start with some of the scaling of the boundary layer turbulence parameters in the wind tunnel that have been developed in the research at the University of Adelaide. The effect of turbulence on flat plate aerodynamic loading, which is with a case study on particularly when the plate is in its vertical upright position, normal to the perpendicular to the flow, and when it is horizontal in stow position, and the effect on lift force. And finally, the impact of boundary layer and flat plate wake turbulence will be mentioned. So firstly, atmospheric boundary layer turbulence. So the way that it is generally decomposed is into a mean component and a fluctuating component, which is related to the turbulence. And conventionally in the boundary layer, turbulence intensity is commonly used in wind engineering design codes for different structures, where the longitudinal vertical components are generally quoted in design codes, where the mean velocity profile can therefore be when looked at in more detail. This is a time series, and the fluctuation, the temporal variation of those velocity fluctuations is defined by the turbulence intensity. However, the spatial variation is also very important for aerodynamic loading. And the Rankin's vortex distribution, shown here with the defined longitudinal integral length scale, is also a very critical parameter that affects the loading. The atmospheric boundary layer mean velocity and turbulence intensity profiles are very dependent on the surface roughness, which was shown in that figure earlier about the cost and how the loading would affect the cost. Generally, a flat desert can be defined by low roughness terrain, whereas a high roughness terrain would be more like a suburban sort of style terrain with buildings and obstacles. Where in this figure we can see there's different layers within the atmospheric boundary layer. So there's the atmospheric surface layer in the lowest 10 to 20% of the atmospheric boundary layer, where the largest variation in turbulent fluctuations occur, where the turbulence intensities and integral length scales are significant. Generally, a logarithmic velocity profile in this region is assumed in neutral stability conditions. And as we can see, one of the issues with, say, for example, a flat plate such as a heliostat is its difference in geometry to a conventional building, which is what the majority of design wind loads, codes and standards are accommodated for. So when you have a structure, a slender, thin-walled structure like a heliostat, that the effect of the turbulent fluctuations is different, especially the dynamic wind effects due to the length scales and the turbulence intensity. So just to define the integral length scale in a bit more detail. So it's using the Eulerian approach, spatio-temporal correlations, where we have this autocorrelation function. And by looking at how it basically defines the average size of the most energetic eddies. And from its in situ measurements, it can be derived by assuming a mean velocity, that the eddy is convected at a mean velocity at that height, and that therefore the temporal time series can be converted to spatial fluctuation, where there are a range of different methods for calculating this integral timescale, including the filtering method proposed by Selesky, which uses a power law fit to the standard deviation of the time filtered velocity flux. However, as you can see, there's quite a lot of scatter and variation in the different methods that are currently used to estimate this autocorrelation integral timescale. And this analysis indicates that there's a range of different methods, and it is in particular in the eddy surface layer, in the lowest 10 meters of the atmospheric surface layer, the variation is generally linear with height of the integral length scale. So it is very important to estimate the length scales for loading on small scale structures in this area. And then, so basically there's a data set that follows similarity theory formulations, where in the surface layer, the integral length scales are assumed to be a function of the surface roughness height, Z0. And then in the outer layer of the boundary layer, they scale on the boundary layer thickness. And this data here shows that basically the turbulence intensity shown by the solid lines and the integral length scale shown by the dashed lines have a counteracting effect, where turbulence intensity obviously increases with decreasing height closer to the ground, whereas the integral length scales have the opposite effect. So it's an interesting analysis to see the relative influences of these two turbulence parameters on the loading on a structure, on a small scale structure below 10 meter height. So we were able to obtain some field data from a very large group of researchers who carried out the SLTEST field experiment, including Hutchins and Rossick from the University of Melbourne, with an array of ultrasonic anemometers to measure the high frequency velocity fluctuations. And it was a very smooth type terrain, flat desert with a mildly transitional rough surface. And using the detrending analysis in Hutchins' paper, we did some further analysis on the integral length scales, and firstly the gust factor. So we looked at, in particular in design codes, typically the World Meteorological Organization recommends a 3-second gust wind speed for design wind loads. However, as can be seen in the figure, at heights below 10 meters, often this can underestimate that peak wind speed, which is correlated to, say, the peak loading on the structure. So therefore, the analysis of the effect of turbulent fluctuations in the lowest 10 meters of the atmospheric surface layer was something that warranted further investigation. So from the analysis of the SLTEST data, in our publication, we showed that the longitudinal component of the length of the integral length scale with longitudinal separations was highly dependent on the surface roughness of the terrain, compared here with a few different semi-empirical models, and also some some data from a data set from Cunahan. And as previously shown, there's a very high amount of scatter in the data for the longitudinal component. And it is very dependent on the upstream terrain conditions, whereas it can be seen in the table here that the ratio of the lateral and vertical components of the integral length scales in relation to the longitudinal component are very consistent across all of the field experiments and semi-empirical models, which indicates that the 3D turbulent structure and the scaling of those components relative to each other is consistent and with similarity theory. So the atmospheric stability. So the data provided so far has been during near neutral conditions or neutral conditions, which is generally defined, for example, with the Hogstrom criterion to be when the stability parameter, the absolute value of that is less than or equal to 0.1. However, that the neutral condition, the neutral stability of the boundary layer only occurs usually during transition periods from the convective daytime boundary layer to the nighttime stable boundary layer, and vice versa. For the majority of the time throughout sunny days, the convective boundary layer is the dominant stability regime. So therefore, some further analysis that we presented at AFMC, at a previous AFMC, was looking at the effect of atmospheric stability on the integral length scales and the turbulence parameters. So the turbulence intensities, and in particular the standard deviation of that velocity component, is very much changes significantly with the stability of the boundary layer, where it can be seen that there is a positive correlation between both the length scale and the standard deviation with in the neutral and unstable cases, whereas in the stable case that there is a less clearer trend there that exists. And also another in design codes and in similarity theory, the ratio of the standard deviations of the span-wise and vertical components with respect to the longitudinal velocity are generally assumed in this region close to in the lower surface layer at heights say below 30 meters, is generally assumed to be roughly constant from these equations, as can be seen by the red line. However, from the analysis in the SLTEST data, we found that this in fact was not exactly constant and did change with height, and particularly at heights below 10 meters, the similarity theory equations can underestimate that ratio of the standard deviations. And furthermore, the effective stability on the length scales with longitudinal separations in the x direction, it was found that both the longitudinal and vertical velocity components were strongly dependent on the height and the velocity profile. And also the stability parameter had a significant effect on the integral timescale, where generally with increasing instability of the boundary layer, the integral timescale increased and is approximately invariant with height, which is an interesting finding. Whereas the Richardson number showed less of a trend, like a less significant correlation with the length scales. And in the figures at the bottom, basically the length scales were also found to increase significantly in the convective case, especially with the vertical component of velocity, which is a value of which is a component of the velocity which in a lot of design codes is not considered, especially for a lot of buildings and wind turbines. So this was an interesting finding that the growth of those turbulence structure, the growth of that with convective conditions, and also similarly in the span-wise component as well, of significant growth. And then when we look at the span-wise Y and the vertical Z separations and the length scales related to them, again, there was increasing anisotropic conditions when the boundary layer becomes unstable. As can be seen by these figures here, where the ratio of the length scale with respect to the height Z increased significantly above 1 during those convective conditions, those unstable boundary layer conditions, whereas a less significant variation was found in the stable boundary layer. They were quite clustered, whereas there was quite a significant range, particularly for the vertical component of velocity, LWX, in neutral case, which was another interesting finding. But overall, the streamwise elongation of the eddies was found to increase with decreasing stability in the eddy surface layer in the lowest 10 meters above the ground. And then the turbulence spectra. So basically, the importance of modeling the spectra in the atmospheric boundary layer is very important to accurately estimate the integral length scales and also the turbulence fluctuations that will affect, in turn, the wind loading on structures. And in particular, the geometric scaling ratio of the wind tunnel model is a significant factor which can suppress some of the low frequency fluctuations, and therefore, so if the model is not scaled at the appropriate ratio, the larger integral length scales, the larger turbulent structures that influence the loading may not be simulated if this model scaling ratio is not carefully selected. So in the figure here, at the top, we can see that from the ESDU data, which uses the modified von Karman form of the spectrum, had two different heights, and we can see that at the larger height of 45 meters, the wind tunnel boundary layer at the University of Adelaide is a closer match in the longitudinal component to a 45 meter height than a 6 meter height, due to this difference in modeling the boundary layer scaling ratio and also the structure scaling ratio. And another interesting finding from this was when you compare the longitudinal component of velocity and the spectrum associated with that with the vertical component, and the fact that it is that there's a mismatch between the longitudinal and vertical component as well, where if a good match with the longitudinal component can be found, often there is a shift to higher frequencies in the other components. So in this case, in the vertical component, we can see here in the wind tunnel boundary layer. And furthermore, the importance of simulating the spectrum can be seen by these three case studies here, where on the left side we have a range of different wind tunnels where an identical cubic model was placed with pressure taps, and then the mean pressure coefficient was calculated, and the variation can be seen from under the same turbulence conditions. The variation can be seen in the observed pressure coefficient. Similarly, with heliostats, when in, say, a 30-degree elevation angle, the maximum lift case, drag coefficient maximum drag case of 90 degrees, and a maximum lift case in stow at 0 degrees. Similarly, a very large difference between the drag and lift coefficients can be seen when simulating the same boundary layer turbulence profiles and boundary layer mean velocity profiles. And then finally, comparing wind tunnel with full scale pressure coefficients here for a rooftop solar panel. Again, there is a significant, a considerable difference between the two. So therefore, to investigate further this scaling effect, this aerodynamic scaling effect, at the University of Adelaide, we have a large-scale wind tunnel with a 17-meter development length and a 3 by 3 meter cross section, where we build up the boundary layer with truncated spires and roughness elements on the floor. We then map the flow with a 2D traverse and multi-hole pressure probe for sampling the high frequency velocity fluctuations in all three components. And then we have a turntable to adjust the azimuth angle of the beta of the wind with respect to the plane projected normal to the surface. And as well as that, the scale of the models we were able to vary in terms of the chord length C of the heliostat, square heliostat surface, as well as the elevation axis or hinge height H above the ground. So to look at some of the boundary layers that we generated, so these were the spires that we used to generate the different boundary layers. And the boundary layer thickness varied between 1 and 2 meters. And we can see for these two larger spire cases here, some of the mean velocities and turbulence intensities and length scales, where the interesting finding was that the turbulence became more anisotropic as the spire base width was made larger. As this restricted the growth of the turbulent structures, especially in the vertical component, and also obviously the limited development length, as well as the limited constraints in terms of cross section of a wind tunnel, that does present a different generation mechanism for the turbulent structures than occurs in the field. So again, with the velocity profiles here are compared with the conventional logarithmic profiles with the logarithmic roughness height. And then also the turbulence intensities here are shown in comparison with the ESDU data bands for these two different roughness conditions of a flat terrain and a suburban terrain, the two extremes of a low roughness and a high roughness type terrain. And these equations indicate the well-known von Karman spectrum, where the ESDU data provides a modified form of this with this coefficient A, which you can see here in its variation with the height to boundary layer thickness ratio. And it was found that the data in our wind tunnel was quite a reasonable approximation with the modified von Karman form of the spectrum over the frequency range of measurement. But as I mentioned earlier, the boundary layer scaling is a very important consideration, which we have investigated in our testing by varying the scale of the models, the heliostat models, as well as generating multiple different boundary layers. And in full scale conditions, the heliostats will range in size from 2 to 12 meters in chord length, and generally from 1 to 6 meters in hinge height, where the boundary layer thickness can be anywhere from 350 to 600 meters, typically in a neutral stability case. However, with different stability regimes, obviously this varies as well. But all of our testing was in the wind tunnel was for neutral boundary layers. And we found that basically the ratio of the full scale to model chord lengths was so in other words, the heliostat size was in the range of 15 to 40, whereas the full scale to model ratio was about 350 for the boundary layer. And as we can see, shown here schematically, let's say for example, two of our different spire combinations and how much of that boundary layer they actually simulate. We use a part depth simulation to try and simulate as close to where the full scale heliostat would be in the full scale condition. The most important part of this testing obviously is the matching of the turbulence characteristics. So the turbulence intensity length scales, the parameters that will influence the aerodynamics of the flat plate. because as we can see, there is often a shift to higher frequencies in the wind tunnel compared to full scale. However, if the critical range of reduced frequencies, FC over U here, can be simulated, we found that this will provide the most reliable prediction of the wind loading. For example, the lift on a flat horizontal plate aligned parallel to the ground, or similarly for the drag on an upright plate perpendicular to the mean flow. But an interesting result from the aerodynamic admittance function here that we found when comparing the vertical component of the spectrum for the lift case and then separately the longitudinal component of the spectrum with the drag case, was that the ideal or the most suitable scaling ratio of the model was 1 to 60 scale for the lift case. Whereas for the when the model is upright and vertical, perpendicular to the flow, it was found that a smaller scaling ratio of 1 to 24 was more suitable, which shows that for the different critical loading cases of a flat plate and its orientation with respect to the flow, the scaling ratio may not be the same for each case. So therefore, each case to most accurately represent the full scale aerodynamics and the full scale turbulence influence on the aerodynamics, each case should be considered separately. A bit of background about the loading and the coordinate system we use for this hinged flat plate, a heliostat. We basically have the two different conditions where we have on the left the operating case, where you have the surface of the heliostat inclined at an angle alpha, elevation angle with respect to the horizontal, whereas in stow position this is aligned parallel, which creates a very large lift force due to the variation in pressure over the longitudinal direction of the surface, and therefore this can create significant loading about the hinge and also the overturning moment. And then, to investigate in more detail the effect of turbulence on the drag and lift for those two cases I mentioned, where you have it one in the horizontal in stow, which is a very important case, but also when you have an upright mirror and the drag force, we actually found that there was a correlation between the longitudinal component of the turbulence intensity and integral length scales, and in terms of the ratio of that length scale with respect to the quarter length of the heliostat of the plate, and that formed like a logarithmic sort of function here for the two different boundary layer cases that we tested. And in contrast, when you look at the plate when it's horizontal, the vertical component became significant and was made the largest the highest correlation with the lift coefficient on the plate, where this was also found to have a logarithmic relationship, but in terms of the vertical turbulence intensity and vertical component of the integral length scale. And further analysis of that horizontal plate again, when the mirror, when the plate is parallel to the ground, through the use of a telescopic pylon where we could change the hinge height of the plate above the ground, we found that the loads could be reduced significantly by 50 to 70% by reducing from the conventional ratio of 0.5 down to say 0.2. By staying closer to the ground, and this was a result of the effect of the build-up of the uniform pressure on the lower surface, and therefore the reduction of that accelerating flow beneath that gap, ground effect below the surface, the windward edge. So that was an interesting finding, as well as the effect here at different roughness lengths. Through analysis of the East to U full-scale data, it was found that the effect of the roughness was quite small at the different values of H over C. When looking at the ratio of the lift coefficient for that case with respect to the lift coefficient for the conventional case of a H over C of 0.5. And further analysis of the data was using the center of pressure, which has been used for flat plates in flat plate aerodynamics, where the normal force over the surface was calculated. From that, the drag and lift force were decomposed, and the hinge moment was derived using the combination of this normal force and also the center of pressure in the longitudinal direction, LPX, assuming that the distribution is average in the spanwise direction, and the variation is small in that direction, that the center of pressure, in other words, the location of where the net force would be occurring on this surface, and its distance from the center, C over 2, where the coordinates are defined here, could then be derived for the different turbulence cases that we have investigated to see the relative influence of both the normal force as well as the center of pressure movement over the surface. And some of the distributions here for some of the load cases of a heliostat, where the elevation angle alpha is defined in this figure here. So the mean and standard deviation distributions are shown here in the two different rows, and it was found that basically the variation over the surface in the longitudinal direction, in the x direction of the flow, that as the elevation angle was decreased towards zero, towards stow, this variation, so this center of pressure movement became larger, which would have implications particularly for the hinge moment about the central elevation axis that was previously shown. And when we look at the analysis of different turbulence cases, so like the turbulence intensity shown in the bottom x-axis, and then the integral length scale shown in the top x-axis of the longitudinal component here, it was found that this center of pressure ratio with the chord length did increase with both elevation angle and with turbulence parameters, whether it's turbulence intensity and integral length scale with both parameters. And it was interesting that when compared with, say, a monoslope roof, which is one structure in design wind codes in the Australian in the ASCE standard, it was found that for a flat plate, in most cases, these center of pressure peak movements did exceed the value for a monoslope roof, showing that a heliostat or a flat plate, an inclined flat plate, is unique in its own geometry and therefore would require its own design conditions and its own parameters. And then also, in addition to all of this on a single flat plate, a flat plate in tandem was placed downstream at a distance x downstream, where this x over c was varied between 1 and 7 here. And for 3 different elevation angles, we also found that the wake generated turbulence by this upstream heliostat would actually lead to further increases in the movement of the center of pressure. As you can see here, where the 0 x over c indicates a single plate, it was found that particularly for the 30-degree case, there was very significant increase in the movement of the center of pressure. And then further analysis that we looked into was the energy containing frequencies of these pressure fluctuations at different points on the surface, and it was found that the hinge moment and also the azimuth moment had quite distinct frequencies, but also in stow, it was interesting that towards the leading edge there was a very significant difference in the magnitude of the pressure distribution, the pressure fluctuations, the spectral energy in the pressure fluctuations by as much as an order of magnitude compared to at other points along that longitudinal line. And the unsteady component of the turbulence is obviously very important for the design of such structures to accommodate for that maximum loading condition and make sure the structure is designed to account for that. And it can be seen here for 3 different cases for maximum lift in stow, maximum lift during operation, and maximum drag during operation, that the distribution of the pressure is a very important component of the design wind loads for the hinge moment, for example, and the overturning moment for different components of the structure, supporting structure, which, as we saw earlier, accounts for a significant proportion of the cost of the heliostat. It was found that the fluctuating load time series as well, through analysis further of the distribution of how the time series of the loading, how well a Gaussian approximation could be used for that, because in previous literature, a lot of the loading assumed a Gaussian distribution, where it was found in some cases that particularly in stow and also for the azimuth moment, that the Gaussian could underestimate the peak load by assuming a mean and +3 standard deviation for the coefficient, the aerodynamic coefficient, whether it's the drag, lift, overturning moment, and so on. So, so this was an interesting finding that we did find that in some cases, some of these critical load cases, a viable distribution or other distributions were more suitable than a Gaussian. So as we can see here, for an example, for the combined stress on the pedestal component, which is this horizontal tube that supports the trusses that are attached to the back surface of the heliostat. It was for different conditions here, for different cases in terms of angles, operating angles, as well as the 2 different boundary layers that we simulated in the wind tunnel. We could calculate the distribution of this combined stress through the von Mises procedure, and it was using the summation of all of the different components of these stresses, the bending and torsional stresses on the pedestal. It was interesting that for one case in particular, during high turbulence, when we have this anisotropic turbulence of turbulence intensity of approximately 26% in the longitudinal component, the Gaussian distribution underestimated the peak. So this dashed line indicates that mean +3 standard deviation value. And it underestimated by 6% in terms of the peak value compared to, say, a viable distribution. So it shows that in some cases, say for example here, the maximum azimuth moment, the torsional sort of moment about the pedestal, it could be found that the Gaussian distribution was not appropriate. And similarly for the torque tube, which I just realized in the previous slide, I had my mouse over the torque tube, but so the pedestal is the component fixed to the ground with a foundation, and then the torque tube is the component that supports the trusses and the heliostat plate. And for this component, similarly, for the case of 30 degrees, so a maximum lift case, again in the higher turbulence boundary layer, the Gaussian component did underestimate again the peak load, but by a smaller amount of 2%. So obviously talking about these critical loading cases, as a summary, I suppose it was these contour plots show the variation with alpha and beta. Beta's on the y-axis and alpha on the x-axis, and it can be seen quite reasonably clearly that when you have a lower turbulence field, so over a flat desert, smoother terrain, and lower turbulence intensity and length scales, the symmetry of the plots is more apparent, and the whereas when you have a high turbulence field, a high turbulence boundary layer, and the flow is more anisotropic, you don't quite see the same symmetry in the flow conditions, and it also obviously as well the magnitude of the peak coefficients is very much significantly increased, as was found when we compared with previous data for an intermediate case of, say, an open country terrain. The dynamic load frequency characteristics was also another component which is very important for the dynamic, vibrational characteristics of a plate, and some analysis of the spectra of the loading and its frequency distribution was investigated, and found that there were some spectral peaks associated with the heliostat wind tunnel model. However, this is very dependent on the size and the structural mass distribution of the model. But it was generally found that a Gaussian distribution was adequate, but again, for some cases, for the operating case for hinge and overturning moment, and then the stow overturning moment as well, it was found that Gaussian distribution wasn't the best fit for that type of distribution. And just quickly go through a couple more slides about the aerodynamics in a field, which has been a more recent investigation. So we're obviously interested, a lot of the work so far has looked at the single heliostat, single plate exposed to a highly turbulent atmospheric boundary layer. However, within a field, all of the heliostats, all the plates are not subjected to the same loading, even though the way they are designed, conventionally designed, is for that case, they're all designed for the same maximum load. So we're interested in looking into how does the interaction of the boundary layer turbulent eddies on the incoming flow with the vortex shedding downstream and the wake turbulent eddies that interact with heliostats further into the field. So obviously in a conventional heliostat field, this spacing, this D over C ratio does vary quite significantly. Closer to the tower, it's very compact and highly densely, very high density region of the field, whereas further away from the tower in the perimeter of the field, this increases to 8. And it was found from some previous studies that the turbulence can increase significantly. The turbulence intensity, for example, can increase to up to 50% within a field, one row of these heliostats. And from our wind tunnel measurements, we also found similar increases in turbulence intensity, where at different elevation angles here, where the black line indicates a 30-degree case at the bottom here, whereas the other two lines here represent the 60 and 90-degree case, the turbulence intensity with respect to the inflow would increase in this near wake region at x over c less than 4 to as much as over 3 for the 30-degree case, and just over 12 for the 90 and 60-degree case, which indicated the breakup of these large inflow turbulent structures and the dominant effect of the wake turbulence in these two very much bluff body type flow regimes. But it was also interesting to see how the flow would decay with that incoming turbulence, accelerating the decay downstream. It was found that at x over c greater than 2, that the spectra of the longitudinal component did conform very closely to the original incoming flow. And then dynamic wind loads on tandem heliostats was another consideration here, looking at how the spectrum of the pressure on the plate downstream changed with and how the straw number was influenced by that dominant frequency. And it was also found again that the straw number based on the chord length of the heliostat increased by a factor of 3 due to that breakup of the large inflow structures again. And then similarly, a reduction in lift coefficient in stow was found from 0.24 to 0.15 between when you have one case, an isolated case, with the tandem case. And then finally, the tandem loads at other angles as well here was investigated, where it could be seen that there's increased turbulence intensity, as we saw in the previous slide, which increased the unsteady component of the loading, the unsteady component on the structure. Even though the mean loading due to the mean velocity deficit was lower, the unsteady component provided a dominant contribution to the peak load, and therefore the peak coefficient of the tandem case actually exceeded the single case for all of the angles, up to 1.5 times for the 30 degree and more than 2 times for the more elevated angles. And then finally in stow, a less dominant change in loading, in peak loading, was observed, where in lower density regions of the field, it was found that the loading would slightly exceed an isolated case, but the majority of the time in stow, the peak loading was found to fall below and actually be quite significantly below the isolated case. So in terms of future applications of some of the research that we've conducted at the University of Adelaide on experimental fluid mechanics, we've identified some different loading cases of a hinge flat plate, which can be used to reduce the wind loads and therefore the cost. But there are also other methods which are very applicable to such structures, such as due to that buildup of pressure near the leading edge, having devices that can reduce the effect of the separation and the wake turbulence on those in-field heliostats is an important consideration, as well as the effect of terrain roughness and atmospheric stability on the dynamic wind loads. And then furthermore, field measurements of the integral length scales with longitudinal, lateral and vertical separations, like a more detailed data set on such variation would be able to verify and also extend some of the research that's been presented. So in summary, we identified that there's a range of reduced frequencies which need to be generated and reproduced in the wind tunnel to be able to most accurately predict the wind loads on a model structure, so a model thin flat plate in this case, in a wind tunnel, for comparison with a full-scale situation in the lower atmospheric surface layer. The lift force could be reduced by lowering a flat plate closer to the ground, basically following the ground effect rule. And peak drag force and peak lift force were correlated with a turbulence parameter, which was not just a factor of the turbulence intensity, the temporal variations of the fluctuations, but also the spatial variation through the length scale to chord ratio. And the drag and lift were respectively dependent on the longitudinal and vertical components of the wind velocity. And then finally, the Gaussian distribution was found to be acceptable in most cases. However, some cases, such as during the azimuth moment and in some cases in stow position, a viable distribution was more appropriate for thin-walled structural components. And then finally, I'd like to just acknowledge the other collaborators in this ASTRI Heliostat project from CSIRO and ANU, particularly Mike, Mick and Joe. Also, I'd like to acknowledge the financial support for this project through the Australian Renewable Energy Agency grant, and also the Centre for Energy Technology at the University of Adelaide. Thank you.
Well, thank you so much, Matthew, for your talk. It's really nice seeing those observations that you had in the wind tunnel results. I think that has some really far-reaching implications. So I think we have time now for questions. So you can either, if you're in the audience, you have a question, you can just unmute your mic and ask it, or you're welcome to write it in the chat, or even kind of do the hand up, like a little method on the participants list, and I'll get to you. Maybe just to get the ball rolling, I had a quick question about, in the observations you found like a little bit of a difference when you had the neutral boundary layer versus the convective versus like the stable, but you didn't have that in the wind tunnel experiments. Do you think it would play a big part, or like in the results?
Yes, I think it would.
Okay.
Yeah, we've only simulated neutral boundary layer cases in the wind tunnel, but I think the scales we found from our data, that scale of that ratio of the integral length scale, say with the chord length of the plate, is very important in affecting, say, the lift and the drag coefficient, particularly in those two cases. And due to the very significant changes in those length scales in the convective case particularly, we would anticipate that would also have an impact on the aerodynamic loading as well.
Okay, that's interesting. Oh, we've got just a question in the chat, so I'll just read that out from Dan. So this is from Dan, asking about, do you see any viability for fluid structure interaction, CFD/FEA simulation?
Yes, I do. I think that the dynamic effects of these structures, as you can see in the video, is a very significant issue with such structures because of their thin-walled sort of nature, and the relative size of them with respect to the turbulent eddies at those heights. It becomes a very significant problem, a significant area of investigation. I think the flutter and aerodynamic flutter and in such cases through fluid structure interaction, through FEA as well. One thing with safe and double heliostats is that those dynamic sort of resonance effects are very dependent on the backing structure and both the size of the heliostat, but as well as the distribution of the mass on that structure. And conventional heliostat designs do vary quite significantly in the way that mass distribution changes. But that would be a very interesting case study, I think, for sure.
We have a question from Vasilis. You nicely described the findings of the ABL, atmospheric boundary layer stability, but can you please give details on how the stability analysis was performed?
Yeah, so the ABL stability is conventionally through the Monin-Obakov theory. And
yeah. So my understanding of the Monin-Obakov similarity scaling is like there's a few different options to pick. Like there's different ways that you can come at this.
There are a few different ways you can approach it, and there's different criteria that have been identified by in the research, and it's been shown that some criteria, for example, this criterion for Hogstrom criterion, sometimes this is not quite strict enough, for example, to identify the near neutral case or the neutral stability, where you actually are in a convective regime when you're getting close to this value of 0.1. So I think, and also it also depends on the reference as well. This is reference height, because these fluxes and values here and friction velocity are generally calculated at that reference height. And depending on the roughness of the boundary layer, that will determine that will often determine the boundary layer thickness and the Reynolds shear stresses and the friction velocity components. And being able to come up with, I think, with a way of nicely being able to be in the correct region of the surface layers, another important consideration when using this theory as well.
Yeah, that's a good point. As in, like, you kind of want to know that you're in the log rate layer region.
Yeah, that's right. Yep.
So I had a question, or two questions from Nadine. So first of all, can you put the heliostats directly on the ground? That's a good question.
Yes, I think I've seen some designs where they have had like a spindle drive or some sort of design where it's actually lowered right to the ground. The issue I think is that I don't know. I think it's just being able to have a stable sort of structure that can easily be maneuvered from that position to an operating position. Because the thing with stow positioning here with heliostats is they may not be in that position for a long period of time, you know, for like say a whole day. They may move between that and operation. So you also at the same time, you don't want to affect your optical efficiency and, you know, operational efficiency of the plant by having a transition to stow that takes a long time. So that's
Also,
another consideration. Yeah.
could it be an issue, sorry, I'm just thinking off the top of my head, that if you did have it kind of on the ground, like would more dust be able to be picked up and just like planted on the
I think,
well, on
yes,
top?
yes. No, I think that's true. And that's another consideration. Soiling of heliostats affects the operational efficiency and therefore will affect the costs as well. And there have been designs that have looked at, say, instead of stowing them with their face up, rotating them so their face is down, which can be another way of reducing that deposition of dust.
So one final question from Nadeem was thinking, why not have more than one leg for greater stability and robustness?
Sorry, can you repeat that?
Oh, so rather than having like a single leg or stand, if you had more than one, potentially that might be more stable.
I suppose if you have more than one, there's more structural cost in all the other components. I suppose the way that the structure, they have a foundation with concrete and the pile that's driven into the ground, and I think in terms of being able to optimize the spacing of the field as well, because these mirrors, as you would have seen at the start, they're spaced quite closely together in the field. So space is a premium, especially close to the tower. So I guess that's another option, because, for example, with PV panels, they're usually on a ballast which has one long row of these of a foundation with the different posts along that row. So yeah.
All right, so if we don't have any other last minute questions, I think we might finish up there. Thanks everyone for coming, and thank you again, Matthew, for a very interesting talk. And we'll be back next week. So